Welcome, everyone. Today, we're diving into objects where time literally stops. I am absolutely thrilled to have you here for this explainer. We're embarking on a true cosmic detective story, tracing our understanding of the universe's absolute most enigmatic objects, black holes. We're going to travel all the way from the realm of abstract, mind-bending mathematics, straight through to the undeniable, stunning reality of modern astronomical observations. It's an incredible story of human curiosity, so let's just jump right in.
Here's our roadmap for today. 1. Gravity and warped spacetime. 2. Anatomy of a black hole. 3. The thermodynamics of gravity. 4. The information paradox. And 5. Breakthrough observations.
Before we get into the heavy mechanics, take a second to reflect on this quote by the brilliant astrophysicist Subrahmanyan Chandrasekhar. He was a Nobel laureate who realized a fundamental truth decades before we could ever actually prove it. He said, "The black holes of nature are the most perfect macroscopic objects there are in the universe. The only elements in their construction are our concepts of space and time." You know, despite their fearsome reputation for total destruction, black holes are just incredibly elegant. They aren't made of some exotic, mysterious material. They're literally universal constructs of pure space-time.
Section 1. Gravity and warped spacetime.
So, to really grasp what a black hole is, we first have to understand the stage it sits on, right? Albert Einstein's general relativity. Imagine space-time as a flexible rubber sheet. If you plop a massive object, like a star or a planet, onto this sheet, it causes the fabric to dip and curve around it. And that curvature, that's exactly what we feel as gravity. Even our own Earth creates a little dimple in this sheet, and that dimple is what keeps the moon locked in orbit around us. Objects moving through space are simply following the curves created by mass. So gravity isn't really just a pull, it's literally the shape of the space around us.
Number 2. Anatomy of a black hole.
Okay, so what happens when a massive star runs out of fuel and collapses, stretching that rubber sheet to an extreme bottomless point? Well, you get an event horizon. Now, I really want to emphasize this. The event horizon isn't a physical, solid surface. You couldn't just land a spaceship on it like you could on a planet's crust. It's purely a mathematical boundary. It is the ultimate point of no return. Once anything crosses this threshold, the gravity is so insanely intense that the escape velocity actually exceeds the speed of light. Put simply, to get out, you'd have to travel faster than light, which, as we know, is physically impossible. And that is exactly why they're black.
The math behind this is just as elegant as it is astonishing. Way back in 1916, while literally dodging artillery fire in the trenches of World War I, which is just wild to think about, the physicist Karl Schwarzschild managed to solve Einstein's incredibly complex equations to calculate this exact boundary. We now call it the Schwarzschild radius. And at the very center of this radius sits the singularity. This is a point of zero size and virtually infinite density. The mass of an entire collapsed star crushed down into this single dimensionless point. Crazy, right?
The scale of these objects is absolutely staggering, and they generally come in 3 types. First, we have stellar mass black holes. These are born from supernova, ranging from around 3.8 to hundreds of times our sun's mass. Then you have the true monsters, supermassive black holes sitting at the centers of galaxies. Our home Milky Way has Sagittarius A star at 4 million solar masses. And it's kind of humbling to remember that our entire solar system is orbiting that exact object right now. But then you look at giants like TON 618 weighing in at an unbelievable, frankly terrifying, 66 billion solar masses. Finally, there are primordial black holes, which theorists believe might have formed in the ultra-dense conditions of the universe's very first second.
Real quick before we move on, let's bust a few sci-fi myths. Black holes are not cosmic vacuum cleaners. They absolutely do not actively suck things in from across the galaxy. If you somehow replaced our sun with a black hole of the exact same mass, the planets would literally stay in their exact same orbits. I mean, it would get very, very cold, but we wouldn't get sucked in. However, if you do get too close, you'll experience a very real phenomenon that astronomers actually call spaghettification. The gravity at your feet would be so much stronger than at your head that you'd get stretched out like a piece of spaghetti, so consider yourself warned.
3. The thermodynamics of gravity.
Now we arrive at a massive twist in our detective story. For the longest time, the rigid rules of gravity and the microscopic quantum world seemed completely, totally separate. But then, brilliant physicists like Jacob Bekenstein and Stephen Hawking realized something huge. Black holes aren't just dead, empty voids. They discovered that the laws governing a black hole's surface area, mass, and spin actually map perfectly onto the standard laws of thermodynamics, things like heat, energy, and entropy. To get why this was such a shocker, you just need to know that entropy is essentially a measure of hidden information or disorder in a system. Bekenstein proposed that the area of the event horizon is a literal measure of its thermodynamic entropy. This entirely bridged the gap between gravity and quantum mechanics in a way absolutely no one saw coming.
If you look at this timeline, it tells an incredible mini-narrative of human progress. Back in 1916, we just had Schwarzschild's pure math. It wasn't even until 1967 that John Wheeler coined the term black hole. Then the 1970s brought us Hawking radiation, finally marrying quantum theory with gravity. And then our technological capability finally caught up. That led to the 2015 LIGO gravitational wave detection and the spectacular 2019 Event Horizon Telescope image. So for nearly a century, physicists were basically flying blind, trusting the math, until our technology finally evolved enough to give us direct, undeniable proof.
Section 4. The Information Paradox.
Now, this intersection of quantum mechanics and gravity didn't just wrap everything up with a bow. It actually created one of the biggest crises in modern physics. According to the no-hair theorem in general relativity, a black hole only has 3 observable properties: mass, charge, and spin. It's called the no-hair theorem because black holes have no complex features, literally no hair, to tell them apart. If a star, a planet, or say an entire encyclopedia falls in, all its unique, complex traits are completely wiped out from the perspective of anyone watching from the outside. But here's the rub. A fundamental rule of quantum mechanics insists that quantum information can absolutely never be destroyed. So think of this as a heavyweight boxing match between the 2 most successful theories in physics, general relativity on one side, quantum mechanics on the other. Which rule actually wins out?
Well, the plot thickens because Stephen Hawking proved black holes aren't completely black. To wrap our heads around this, we need to know that the vacuum of space isn't actually empty. It's more like a boiling soup of virtual particles constantly popping into and out of existence. Near an event horizon, occasionally one particle falls in while its partner escapes. That escaping particle literally steals a tiny bit of energy and mass away from the black hole. This means the black hole is slowly shrinking or evaporating via this Hawking radiation. But if the black hole eventually shrinks and vanishes completely over an unimaginable amount of time, where does all the information of the stuff that fell into it actually go? Believe it or not, physics is still fiercely debating this exact question today.
Section 5. Breakthrough Observations.
While the theorists are still wrestling with that paradox, the experimentalists went ahead and delivered a triumphant final act. In 2015, humanity literally heard the universe shake. The strain data from the LIGO detection showed ripples in the very fabric of reality itself. These were caused by 2 massive black holes spiraling together, merging, and ringing down into a single entity over 1 billion light-years away. The observed waveform matches Einstein's predictions perfectly. I mean, we literally built an instrument sensitive enough to measure a spatial distortion smaller than a fraction of a proton. Just incredible.
I want you to just think about the number 3 for a second. In that single 2015 merger, 3 solar masses, that is nearly 6 billion trillion kilograms of mass, were completely converted into pure gravitational wave energy in just a tiny fraction of a second. To put that into perspective, for that brief, fleeting moment, the power radiated by this completely unseen collision was more than 10 times greater than the combined light power pouring out of every single star and galaxy in the entire observable universe, all from 3 solar masses.
And man, the floodgates really opened after that. The Event Horizon Telescope accomplished the impossible by linking 8 radio observatories across the globe. They effectively turned the entire Earth into one giant satellite dish just to capture that iconic bright accretion ring around M87. Meanwhile, we've used ALMA telescopes to peer right through thick cosmic dust, proving our own Milky Way's black hole blows out these hot, glowing winds. We've even meticulously tracked the exact orbits of stars zooming around seemingly nothing at the center of the Milky Way. That proved our galactic center hosts a supermassive black hole, a stunning discovery that won a Nobel Prize and ties right back perfectly to those early gravity concepts we started with. After all this time, we have finally brought these dark behemoths into the light. The evolution of black hole science proves that human curiosity can illuminate even the absolutely darkest corners of reality. It's truly breathtaking how far we've come. But, as always in science, every single answer just unlocks a brand new puzzle. We can now actually hear the ripples of their cataclysmic collisions, and we can directly see the glowing shadows of their event horizons. So I'll leave you with this to ponder. What profound secrets of quantum gravity are these magnificent objects hiding next? Thank you so much for joining me on this explainer today. Keep your eyes on the stars and definitely stay curious.